Okay, and now I'll turn things over to Scott.
So
Scott.
thank you to the organizers. Thank you for letting me talk about the four-color theorem in a conference talk for Lou's 80th birthday. And many of you may not know this, but Lou spent a lot of time. There's a lot of really beautiful papers that Lou wrote on the four-color theorem, and he's been a really big help in my life in terms of being encouraging and being sharing with his ideas. I think of him almost as like if a full professor could have a thesis advisor, Lou would be it. So um, so happy birthday, Lou. And today I'm going to talk about a new way to prove the four-color theorem, and I'm going to show how to use gauge theory to do it. Throughout the talk, I've done already, if you open up your chat, what I did was I included a bunch of papers, kind of the free versions of the papers, not behind any paywall. So like archive papers of the different papers I'll be talking about throughout the talk. I might just refer to them by their numbers in the talk. So if you're wondering why I'm putting 7 on there, it's because I'm talking about Amit Kumar's paper, for example. Okay, so hold on a second. All right. So first of all, you should always start off with what the four-color theorem is. It's every plane graph, and I'm going to think of them as trivalent graphs. So at every vertex, there's 3 edges. Without a bridge, bridges just mean that there's no graph. Oops. There's no graph 1, and then there's a bridge to graph 2, where they can be separated by deleting the bridge. So in any trivalent graph without a bridge can be 4-phase colored. That means that you can put 4 colors in each of the faces of the graph, so that along any edge you don't have red and red. You'll always have to have red and blue or red and green. So this is obviously a very famous theorem, and I'm going to take a kind of cloaking style approach to this, and that's partially because we're going to have people that don't think about the four-color theorem that much, but also because it's a great way to introduce the terms that I need. So as we go along, I'm going to be introducing terms using kind of simple pictures. But the problem itself dates back to the 1850s. Took 125 years to solve, and it was the first computer-based proof. So the thing about the computer-based proof is that it is awesome. It is truly a beautiful proof that led to the introduction of computer science and mathematics and all sorts of wonderful things. But at the same time, it gets kind of hard to see the actual structure behind what's going on, kind of underneath the engine. So I want to make the claim that we are at the beginning of the end. And I'll show you what that means as we go along, improving the four-color theorem without computers. And that the mathematical structure needed to prove it comes from a TQ of T that's very similar to Havana homology. And I'll give you some examples of that, but I'm going to suppress the Havana homology from the talk. I'll stay at the level of kind of a Lie-like homology. But it's there, and just know that it's there. In other words, so originally when Apple and Hecken proved this, they said that 4 colors suffice. And so I'm upgrading that. I'm saying that the universe demands that 4 colors suffice. So let's get into it. So to explain why we need this, we need to take a step back all the way to a while back ago, before all of us were born. And the 4-color theorem is very hard to prove. I run into this problem in trying to explain this to other mathematicians. I run into 2 pitfalls. One is that you're not familiar with, you haven't generated 100 wrong proofs of the four-color theorem yet to know how hard it is. And I'm probably on 200 at this point. And the other issue is that when you do have something, then people kind of look at you like, oh, sure you did. So because it's such a popular thing and so many people have tried to prove it in the past. So to give you some idea, the first thing I would say that it took me when I proved that there was an exotic CP2 blown up 3 times. That took 5 years. Like I was playing with those manifolds for 5 years. They're basically S1 bundles over mapping class groups of mapping class tori. So it was in playing with those objects that I finally learned the way that basically all these manifolds are constructed now, which everybody would know by the word Luttinger surgery. But if you go back and you look at what I did, it was 5 years of effort. For this one, I'm on year 7. So if that gives you some sense of what I mean by hard, it's hard. Let's start. Let me see if I can grab this. Let's start out. So it starts out easy enough. So in the beginning, Kemp showed that there was at least, ooh, that's interesting. Delete that. So Kemp showed that there was always at least one bigon, trigon, quadrilateral, or pentagonal face that must appear in every trivalent graph. And that's actually very simple. You just use Euler's characteristic, and you compute, and you show that there cannot exist a graph with hexagon faces, trivalent graph with hexagon faces or more. So that one of these 4 pictures has to show up. This became what is known as the first unavoidable set. So, like if you read about the 4-color theorem proofs, you'll hear about unavoidable sets and reducibility and so on like that. I just want to show you something really simple. This is an unavoidable set. You cannot avoid these 4 pictures showing up in your in any trivalent planar graph. At this point, for the not theorists, you should be thinking of these things as tangles. And they'll start to look more and more like tangles as we go along. Okay? And then Kemp then proceeded to show that if gamma was a minimal counterexample to the 4-color theorem, then it could not have a bigon, trigon, quadrilateral, or acclaimed pentagon face. And that's a contradiction, because it's supposed to have one, but it can't have one. So that says that no minimal counterexample exists, therefore the 4-color theorem is true. So just as a simple example, let's take the bigon. So suppose a bigon shows up like that in a minimal counterexample. Then what you do is you replace it just by getting rid of it. And now you have something with fewer edges and fewer vertices. So since it's smaller than the minimal, it has to have a 4 coloring. So if we have a 4 coloring, then we can give a coloring for the whole thing. And at that edge, it might look like that, red and yellow on one side and yellow on the other. But if there's red on one side and yellow on the other, then you can go back to the original one, and that's still red and that's still yellow. And now you can fill that in with green. So this is the basic idea. And this is called the reducer. And he would say that the bigon was reducible. In other words, it can't show up as in a minimal counterexample. The same thing works for a triangle, because you have 3 colors around the edge, and then you have the 4th color to plug into the middle. But for a foregon, we start to have a problem. So let's see what happens with the foregon. And again, this is, if you've seen this before, I understand, but I'm also using this to describe the following word. So suppose you have something that looks like this, and you reduce it. So that's got smaller, that's smaller. And you color it so it's got red, green, blue, yellow. And you know, if it's you know, if it's green, no problem, because then you can just put yellow in the middle. So no issue there. But if the little thing ain't is it working? But if it turns out to be that you used all four colors, and you go back to the original, well, now you got a problem. Because you can't put what you want to put in for that last color. However, you could look at a chain of blue, red, and if the chain looks like that, no big deal. Because the next thing you can do is switch, what's called a Kemp switch. You can replace this chain, and you can, if this is the only red blue combinations, you can replace the red with a blue and the blue with the red, and you just switch it all the way down. And that would be another nice four coloring. But now I've got three colors around the edges, and I can put in red into the center. So that's called a Kemp switch, where you take a pattern of a chain of two colors, and it may not look like a chain necessarily, it might spread out into the graph, but once you as long as the chain doesn't bump up against the other erase this. Oops. Sorry. There. As long as they don't chain up like this, now you have a problem, because now when you do the red-blue switch, you're just gonna interchange the red and blue at the bad spot. And so, but now you have something new, which is the yellow and the green have to be separated from each other. Which means that, you know, when you do a yellow-green, it can't puncture into this area. In other words, they have to keep separated. And now you can do a Kemp switch on the yellow-green and get the answer. So using this technique, he was able to do bigon, trigon, fourgon, and he used the same technique for the fivegon. But here the problem with the fivegon is that the colors can go past each other. And so in 1890, Haywood showed that even with reducibility, even with Kemp switches, you cannot prove that that the fivegon is reducible. All right. So what did they do? So Wernicke in 1904 took the pentagon, took it out, and put these two pictures in. So if you could find a double pen and a pentagon with a hexagon, then for that that would also be an unavoidable set. In other words, you would always have to find at least one of these pictures, and I'm including the bigon, trigon, and fourgon. Another one that's famous is Franklin's unavoidable set, which puts those pictures in. And the question is can any of these unavoidable configurations be shown to be reducible? In other words, if you reduce them, could you color them and then recolor the original? And by reduce, of course, we're taking a smaller picture, a smaller configuration. Therefore, it would have to be smaller than the smallest in the minimal counting sample. And okay, maybe one of these you can use a chem switch to show that everything works. And the answer is no. So these don't work either. They also suffer from the same problem that Kemp's configuration, the pentagon. You get yourself into a bind. However, Birkhoff in 1913 showed that you can reduce the Birkhoff diamond. And the Birkhoff diamond is just 4 adjacent pentagons, which if you take the dual, it looks like a diamond. So I'd show you the diamond just so you know where the term diamond came from. We'll be using this picture, the 4 pentagons. And the reducer that you replace, so you replace this with that picture, and then you suppose that that has a coloring. And with that coloring, then you ask, well, can I use the coloring that's coming from outside? Can I push it in? And if you look at this, for example, you see that you have to use a Kemp switch. So keep track of this. The Birkhoff diamond is reducible using Kemp switches. You need the Kemp switches to use Birkhoff's original proof. And you can see that because, if I make this yellow, this has to be yellow. And if that's yellow, this has to be green. But if that's green, yellow, green, blue, that has to be red. And now you've used all 4. So you can't put anything there. But, for example, if you create a red-green path and it happens to link those up, now you trapped your blue-yellow, and you can do a Kemp switch. And I'll let you do it as an exercise. If you switch up those two, then you can start to fill it in. And the point is and this turns out to be true as we go along in the descriptions, right? That the really hard things to show reducible are the really small ones. As you get more and more edges and more faces, it gets easier to show reducibility. And I say that easier is in quotes. I don't mean to imply that it's not impossible. So that's what I mean by easier. One way to describe this is that Haken said that Hesh, who came up with the trick for building unavoidable sets, really beautiful idea. He could recognize reducibility by just looking at a picture about 80% of the time. So that's what I mean. Like you once you get really into it, you start looking at it and you go, oh, that one's reducible. No, that one's not. And you can kind of get a feel for it. But the search was on. So the search was on. So it now took another 64 years in which they were trying to build unavoidable sets that could be shown where every picture in it could be reduced. And if that's the case, that would be the 4-color theorem. The first one, of course, is Apple and Haken in 1977 using their computers. And then came along Robert, Sanders, Seymour, and Thomas in 1997. And oh, by the way, again, these are like some of these are in the chat. So this would be, I didn't have an easy one for that. This would be paper 8. Or Steinberger with a bigger set, but has some special properties. So those are the 3 valid proofs of the 4-color theorem. What's interesting to note is that if you're going to start building these unreducible sets, except for the bigon, trigon, and fourgon, every reducible set starts with the Birkhoff diamond. And there you see the Birkhoff diamond. It's shown in its dual form. So that's 4 adjacent self-adjacent pentagons, or close to be adjacent pentagons. But this one here, this one here is 3 pentagons and a hexagon. This one here is 2 pentagons on the side and 2 hexagons in the middle, and so on. So you see that they all start to get bigger in terms of the tangle that happens. So if you're at this point, you're thinking, I'm a topologist. What does this have to do with what I'm thinking about? I would just say that if there's one thing you leave this talk with, it's that is that I want you to think in terms of ways that you could attack the the smooth Poincare conjecture could maybe someday look like this. In other words, imagine that you have a smooth homotopy force sphere, and there's a way to characterize it. There's a way to represent it. And if you represent it, say via a knot, maybe, or maybe via some sort of triangulation, as Manturov was showing in the last lecture. And suppose further that whenever you represented a homotopy, a smooth sphere, that it always had to have certain configurations in it. And you could show that were unavoidable. And that for each one of these unavoidable configurations, you could show that there was a trick that you could do with the configuration that then made that homotopy force sphere standard. And then the search would be on, much like in 1913, the search would be on to find what is that representation, how do we represent it, and then what are those list of unavoidables, and then can those unavoidables be turned into, can you do something with the unavoidable configuration to turn the manifold into a standard one? It's not that far off. Haken is well known as a topologist, for example, and he claimed to have 98 out of 100 cases that if you could only prove the last two cases, you would have proven the three-dimensional Poincare conjecture. So it's not inconceivable that this is a way of thinking about these things. So just keep that in the back of your head as a maybe that's something that you can think about for the rest of the talk. Okay. So in 2024, last year, we proved, at the very end of last year, we proved that the Birkhoff diamond is reducible without using Kemp change switches. So this is the first new proof of reducibility in 111 years. And we actually show a new way of doing the reducibility because we don't have Kemp changes to do the reducibility with, or at least not yet. So what I'm going to do, so here's the main theorem, theorem 4. You replace the Birkhoff diamond with its reducer, so it's going to look like that. And and of course, that's a smaller planar graph. So that smaller planar graph now has a 4 coloring. And what state reducibility means is that I can now find 3 face colorings on some surface of that reducer where that new graph is actually a 1 skeleton of some surface. And that surface has a 3-face coloring, not a 4-face coloring, a 3-face coloring. You're only using 3 colors. And using that 3-face coloring on that surface, I can now produce a 4-face coloring on some surface on the Birkhoff diamond. The one with the original Birkhoff diamond. So that's what I mean by state reducible here. So if gamma prime is the reducer for gamma and gamma prime is 4-face colorable, then gamma itself is 4-face colorable. So the rest of the talk will be explaining how these words work. But notice that we're not using, so you'll see in the actual idea, we never use a Kemp switch. Now, remember that the Birkhoff diamond shows up as the first example in all of the configurations of the unavoidables. It's at this point that I can say pretty confidently that we could just crank up a really fast computer and do all the calculations for all the 632, say, configurations that remain in the RSST set. But there's something that's more exciting, and I'll get to that. But first, let me just talk a little bit about the history of where this problem came from. So in the past 10 years, there's been 4 attempts to prove the 4-color theorem using gauge theory. Kronheimer and Rothkos with their Instanton homology, which is a beautiful paper. Havanoff and Roberts, which motivated Havanoff and Robert through another fantastic paper. These are 5 and 6. So this is the start with 5, and that one's 6. And then there's ours, which is really topological quantum field theory. That's 2. And then one of my students, Amit Kumar, came up with yet a 4th way of doing it, using TFTs with defects. That's 7. So if you're interested in, go take a look at those. They're all, well, not mine, but the rest of them are beautiful papers and very interesting and a lot of fun to look at. All of them state an equivalence, though. They say the 4-color theorem is true if and only if some other theorem is true. And the problem is that some other theorem so oftentimes is as hard as the 4-color theorem. In other words, you just replace one bad thing with another one hard to prove thing with another hard to prove thing. And in our case, that's the existence of a spectral sequence that starts with a homology theory that is non-vanishing, can be shown to be non-vanishing, that when you get to the E-infinity page, that the E-infinity page also doesn't vanish. And so, not easy. It's just a really hard thing to prove in general. But what I'm trying to say here is that our Birkhoff theorem is really a different beast. In other words, it shows that you can prove the 4-color theorem directly from our homology theories. And it uses our weakest one. So you have to imagine that, again, there's a spectral sequence in which the E1 page is like it looks kind of like a Havanoff homology. And then the E-infinity page looks like a Lie homology. Of course, by the time you get to Lie homology, the Barnatan quote that it's very uninteresting, but it's very interesting comes to mind. It's at the top. It's at the E-infinity page that I'm going to show you everything here today. Okay, but it's sitting on top of a quantum engine that's really quite exciting. The main point is that this is the first time in 10 years where we can actually prove something positive using some of the gauge theory techniques. So what that means is that I want to encourage everybody to go look at all 4 of these ideas. They're all, there's a real reason to look at these ideas, and I'm hoping that this gets more people excited about looking at all of them, not just ours. Okay, so what is our theory? So I've got 12 minutes, and I've got 4 slides, 3 slides. I don't have that many more slides. So it's based on a special TQFT, 2 plus 1. And what you're going to do is you're going to replace circles with vector spaces. The vector or algebras. The algebra that I'm going to use is kind of like the Lie homology version. So V hat in general looks like this. You would join X, where N is the number of colors. And what you can do is you can write a basis for that vector space in a new basis, C0 through Cn minus 1. Those turn out to be the colors of the system. That algebra has a really nice, has some multiplications, co-multiplications. It also has a shift operator, which shows you that it doesn't behave at all like Havanoff homology. But I'm using things by analogy, right? And Ci tensor Cj has this really nice property that C0 tensor, say C1, if you multiply them, you just get 0. So if I'm multiplying red times blue, I get 0. If I multiply red times red, I get red again. And that's the main thing that allows us to recognize that we're actually talking about colors. So let's do an example. Here, if you look really closely, you see that it looks like doing a 0 and 1 smoothing. And in fact, that's what's happening. In other words, we're going from a 0 smoothing, and now we're doing a 1 smoothing, where that's a virtual crossing. That's not a 4-point, four-valent vertex. Okay. And let me erase that. Erase that new thing. Oops. All right. So if I look at these circles here, they are the faces of my theta graph. And when I do put in a twist, I'm actually combining circle, like this one is combining circle 1. This one right here is combining circle 1 and circle 2 and leaving circle 3 alone. So that's a multiplication between circle 1 and circle 2. And if I was to take circle 1, so if I had circle 1's red, tensor, say blue here, then the multiplication of that, at least in the first position, would be C naught times C naught red tensor red, which is C naught again. And then the second component multiplies 2 and 3, that would be these two, that would be 0. And then the third component multiplies 1 and 3, and 1 and 3 1 and 3 would be these two, that would be 0. So you see that element in the chain group goes to something that's not 0. But what does make things go to 0 is if you have 3 different colors. So C1 tensor, say C3. And now you do 1 and 2, and that's 0. 2 and 3, and that's 0. And 1 and 3, and that's 0. So what's showing up in the kernel of this differential, is a proper 4-face coloring of the theta graph. So in this case, the dimension right here, the dimension of the 0 homology is just going to be in the 24, because we have 4 different colors for the outside face, 3 colors for the left hand, and 2 left over in the other spot. So if that's interesting, that's how all this stuff works. Now expand this out to an entire hypercube, and there's chain groups just like as in kind of Havana homology, and we work out in paper. Again, this is all paper 2 in the chat. Shows that all of that's well defined. And in general, the dimension of all of them, if you sum up all the dimensions of all the homologies, that's equal to the number of n-phase colorings on state surfaces where gamma is the 1 skeleton, where the graph is the 1 skeleton. Which time do I have? Okay, 7 minutes. So all right, where are the state surfaces in this? Well, these are so Ian Moffat often calls these partial Petrel graphs. They're ribbon graphs, and I'm showing you how to glue in the disks. If I glue the disks into 1, 2, and 3 there, I'm going to get a sphere. So this is just this particular graph right here is just a nice way of representing a sphere. In this picture right here, though, I'm gluing in 1 disk. There's a disk there. But in this case, I'm gluing in a Mobius band, a disk into a Mobius band. There's the place where the Mobius band is. So when I glue in there's only 1 boundary component there, and when I glue in a disk for that boundary component, I'm actually getting an RP2. So what I'm actually looking at is a sphere and then a set of RP2s. I think these are probably, I forgot, I'd have to do the calculation. These are either RP2s or Klein bottles, this entire column. And then if you think really hard about this for a little while, that's actually a torus. And so what you're actually seeing is when I say end face colorings, I'm actually now talking about putting colorings on different surfaces in a state, in my hypercube. Okay. It's really kind of the key essence is that the reason why we call them state surfaces and state graphs instead of partial Petri is because we're really talking about how these things are sitting in the hypercube of states. And so what you have to imagine is that for a minimal counterexample, there's some with 60 edges, there's going to be 2 to the 60th number of these surfaces. And in the surfaces, I'm going to ask, can I color them with three colors? Can I color them with 4 colors? The faces of all these surfaces, all 2 to the 60 of them. And that should give you a clue right there. Like already you should know, oh, we have way more things that we can play with now in the 4-color theorem than we had before. Before we just had 1 graph. Now we have 2 to the 60th number of graphs. And this is beautiful. If the graph you start with is already 4 colorable, that means that there's some surface in there that has 3 face colorings. And you only need 3 colors to paint all the different faces on the surface, so that each face only rubs up where every face rubs up against another face, it's red and blue instead of red and red. So that's what this tells you. So here's the basic idea for proving 3-face coloring or state reducibility. So take your Birkhoff diamond, replace it with the minimal counterexample, or in a minimal counterexample, sorry, replace it with R, which is smaller. That means that to get gamma prime, that's the reducer. Well, now gamma prime is 4-face colorable. And that means by Penrose, in an absolutely gorgeous paper, everybody should read it. You'll see almost all of modern TQFT stuff coming right from the paper. He shows that, well, he doesn't know about our homology, but the Euler characteristic of our homology is equal to the Penrose number at 3. And he shows that that's not 0. So that means that in gamma prime, in our reducer, we have surfaces with surfaces high genus, maybe unorientable, but there's some genus G surface or some unorientable surface that can be 3-face color. And then the question is can I take that 3-face coloring and build a 4-face coloring back on the Birkhoff diamond? Because if I can, back on the Birkhoff diamond, then that means that my 4-face or 4-face coloring homology is non-trivial. But Ben and I proved in 2023, this is paper number 3 again, paper number 2, that is an extreme invariant. If any homology is not 0, then the graph is 4-face colorable for a planar trivalent graph. In other words, any minimal counterexample, if there really was a minimal counterexample to the 4-color theorem, then our homology has to vanish completely. So if I can show that it doesn't vanish, boom, it means that we can prove that means that the original graph could be 4-face color. So once again, you should be thinking, oh wow, we've got way more states to play with than even Birkhoff did. Okay, so here's a quick example of how to do that. So imagine, we got 2 minutes, we got one more slide. So imagine that here's the reducer. And so now I know that there's a 3-face coloring on it. And the 3-face coloring is going to have, like greens here, and there might be greens there, right? It's going to be really complicated. And there might be, things like, there's all these faces that are interacting. what I'm going to do is just delete them all. Because if I can fork face color just this picture, then I just bring along all the other colors for free. Okay. So then I take out my reducer, I put in my Birkhoff diamond, and if I did this right, I start trying to put in, well, I can put a green in here. And if this looks like I'm playing with links, it's because I am. Oh, and by the way, this is these are multi-virtual things. These diamonds here are loose diamonds that we'll talk about later today. Okay. And you can think of this as now a big kind of linked set of links that I'm coloring different colors so that when they interact, they have to be different colors. I've got a blue that I could do here. And I've got red that I can do here. Red can connect with that red. This red can go through here. And now I see I've got a problem that if I try to use blue this way, it's got to go like that, and it's going to cross. Now that's going to be a blue, and that's going to be an edge where blue and blue are on the same side, on both sides. So that's a fault. That's not an example of not a coloring. But this is the aha moment. Aha moment is I have a fourth color. The fact that I could do this on with a three face coloring means I've got a fourth face color that I play with. So let's switch to yellow. And when I switched to yellow, I had a blue, the blue had to go here. When I switched to yellow, well, as long as the red and the blue don't interact, ta-da. I can replace that red and that blue with the yellow, and now that's a four-face coloring. That four-face coloring now translates directly into a four-face coloring on the original graph, i.e. I've just four-face colored the original graph. So state reducibility says that for every three-face coloring on the reducer, I can get a four-face coloring on the original graph. And as I say right here, no chem switches. Now there are chem switches. Think about it. There are chem switches. You've got these colorings on some big high genus 100 surface, right? And I could take chains of blue, red, blue, red, blue, red, blue, red, blue, red, but it's going to go all around the surface, and right? And then I can do a switch on those blue, red, and switch them all the way back. So I still have the ability to do chem switches. I just didn't need to. I never used them. So that brings us to the final page, which is hopefully I've convinced you that if you start with the Birkhoff diamond, it gets easier. And I put easier in quotes because it's not easy, but it's easier. And if you want to, so what I mean by this is the 633 of RSST. The 633 of which we just showed. So the original Birkhoff showed that you needed chem switches. So this is with chem switches. And we just showed without chem switches. Now, this is impossible with, it was actually proven by Haken and Apple and Haken that it was impossible to prove these with chem switches. Like they actually don't, anything that's smaller than the Birkhoff diamond is impossible. So this is, you should think of this as harder. It's getting harder going this in the direction to the left. with Kemp being insane. I just call that the insane one. Right. But we can add Kemp switches now back into the picture. So while Ben and I have worked it out, without Kemp switches, these are still impossible. But with Kemp switches, we think that this is the beginning of the end. In other words, Birkhoff in 1913 was the beginning of the end for using with Kemp switches, and 2024 was the beginning of the end with using Kemp switches, but with state reducibility as the new thing that we've introduced. Now, so here's a good conjecture. The triple pentagon, i.e. this one, is state reducible with Kemp switches. Oop, I'm going over. I'm almost done. So if you throw in the Kemp switches into the mix, where you put, now you're in the states, and then you find something maybe on a reducer, now you can still do a Kemp switch on that, and then use that to actually four color the 3-pen. So we figured that that's the way that we're going to see. Will it take what is that, 84 years? No. I think the question mark here might be 2030, something like that. You start to see new proofs that can solve these smaller problems, the smaller configuration problems. Why would that be good? For example, if you do the Franklin, this 3-pen, then the 3-pen shows up in 148 of the our RSST configurations, so you can eliminate them. So you just, by showing 3-pen, you just eliminated 25% of all of them. And if you get it all the way down to the pentagon, you just eliminated all of them except for the pentagon. In other words, you get back to Kemp's original proof. So while I think these are doable using the Lie homology versions of what we're studying, I think you're going to have to dip into. I think that's possible, but only after you get down to the Havana homology. You know, the Havana homology that detects the unknot kind of strong quantum theory, and then that will eventually, maybe 2035, we can solve that problem. Okay. Thank you. Happy birthday.
Great. Thank you, Scott. That's great. I'm going to turn off